For this last video of Chapter 15, we're going to take a look at the effects that salts can have on the pH of a solution. As you remember from Chem 101, a salt is going to simply be a combination of a cation and an anion. Okay, and some salts, when they're dissolved in water, are going to produce acidic solutions, some will produce basic solutions, and some will even produce neutral solutions. And our goal here is to be able to predict what type of solution is going to be produced based upon knowing what the identity of the cation and the anion are. So the first thing we're going to look at is the salts that produce neutral solutions. Okay, so in order for a salt to affect the pH of a solution, it must react with water to either produce hydroxide or hydronium. Okay, so for a salt to produce a neutral solution, neither the cation or the anion is going to react with water. And this typically happens when we're looking at cations that are either group 1 or group 2 metals. And anions that are the conjugate base of strong acids. Okay, so if you think of all the different strong acids out there, and then subtract a proton away from that, then you'll see all the different possible anions. So that would include things like chloride, bromide, iodide, sulfate, it should be bisulfate, chlorate, perchlorate, I should say, and nitrate. Okay, so if the cation comes from group 1 or group 2, such as something like sodium, and the anion comes from, one of the conjugate bases of strong acids like hydrochloric acid, okay, what we get is a salt that's going to produce a neutral solution. Okay, in fact, if we add sodium chloride to water, we simply wind up with solvated sodium cations and solvated chloride anions. Okay, the second thing we're going to look at, or second type of solution, is basic solutions. So there are some salts that when we add them to water, they will produce a basic solution. Okay, now, in order to produce a basic solution, what this means is that either the cation and or the anion have to react with water in a way that is going to produce hydroxide ions. Okay, so typically we're looking at cations that are group 1 or group 2 metals, and anions that are the conjugate bases of weak acids. Okay, and this should make some sense here, because when you think about it, the conjugate base of a weak acid, it's still going to have a potential to try to pick up a proton, because we know that those reactions where we have an acid added to water, a weak acid added to water, that the reaction doesn't go to completion, so we still see some protons being sucked up by the conjugate base. Okay, so an example of this would be something like sodium fluoride. Okay, now if I take sodium fluoride and I add that to water, I get sodium cations that have been solvated, and I get fluoride anions that too have been solvated. But here's the thing, while sodium does not interact with the water at all beyond that, the fluoride, being a weak base, can react with water, and that will produce a little bit of hydroxide. Okay, which is going to make the solution basic. Okay, the third scenario is going to be those salts that produce acidic solutions. Okay, and this usually happens when the cation is either a transition metal or it's a ammonium salt. I'm sorry, I should say an ammonium cation. So NH4 plus. Okay, and the anion is the conjugate base of a strong acid. So for example, if we have something like ammonium chloride and we add that to water, we're going to see solvation take place and ionization, where we get solvated ammonium ions plus solvated chloride ions. But we have to remember that ammonium is a weak acid, which means if we were to mix this with water, to some extent we're going to get the production of hydronium plus ammonia. Okay, and this formation of hydronium is what's going to drive us towards having a more acidic solution. Another example would be the reaction of something like aluminum chloride. If I take aluminum chloride and I mix that with water, actually let's show it like this. Okay, what ends up happening is we form aluminum chloride, okay, with an OH attached to it. And overall we have a negative charge, and we produce a proton, which ultimately gets transferred to water and becomes hydronium. And again, that's going to make this whole solution acidic. Now, if we go back and look at the first three types here, okay, we saw that in the case of the neutral solution, we had a cation that did not affect the pH, and we had an anion that did not affect the pH. And that's because neither one of these hydrolyzed in the presence of water. If we go to the basic solution, we have cations that are not going to be to affect the pH of the water, but we have an anion that does. In the acidic solution, we have an anion that does not affect the pH, but a cation that does. Okay, but what happens if we have a cation and an anion that can both affect the pH of the solution? In other words, both the cation and the anion undergo hydrolysis. Okay, so we'll say both ions hydrolyze. Okay, an example of this would be something like ammonium fluoride. If I take ammonium fluoride and I add this to water, I make ammonium that has been sulfated, and I make fluoride that has been solvated. But each one of those individually can react with water. Okay, so ammonium plus water is going to give us hydronium plus ammonia. Likewise, fluoride, if it reacts with water, will give us HF plus hydroxide. Okay, so we have one part of the compound that is making things more acidic, and one part of the compound that's making things more basic. So how do we predict this? How do we know how this is going to behave? Well, it all comes down to which one of these two things, the ammonium or the fluoride, is better at its job. Which one of these is going to have the bigger effect on the concentration of its particular component of that acid-base system. Okay, and the best way that we can go about figuring that out is by looking at the Ka value and the Kb value for the two compounds, or I should say for the two components here. Okay, so the Ka for ammonium is 5.6 times 10 to the negative 10th. Okay, and the Kb value for fluoride is 1.4 times 10 to the negative 11th. Okay, and remember, the larger the K value, the more the products are going to be favored. Okay, now it doesn't look like this, but the ammonium is actually a stronger acid than fluoride is a base. Okay, in other words, if I have this kind of balance going here between acidic and basic, ammonium is going to win this. So overall, the solution is going to be acidic. So if the Ka of the one component is greater than the Kb of the other, then the solution will be acidic. However, if the Ka is less than Kb, the solution will be basic. And on the off chance that Ka equals Kb, the solution will be neutral. Okay, so we should be able to eyeball whether or not a particular salt is going to produce an acidic, basic, or neutral solution.